Welcome everybody to our Gamma seminar. Today we have the pleasure to guest Vladimir Salnikov from the Generalized and the La Rochelle University. He's going to talk about generalized geometry for modeling mechanics. So Vladimir, it's a pleasure to have you here. We are really, really happy that you accepted our invitation. So please, the floor is yours. You can start.
Thank you, Javi. So thanks for the invitation, first of all, and as usual, sorry for me being very slow to reply, but in the end of the day, I replied. And I'm happy to be here. Okay, I gave a title that doesn't oblige me too much, at least in this community. You see geometry, mechanics, you somehow know that there are a lot of links. By generalized geometry, I will mostly mean Dirac structures. And I also think that some of you might have heard at least parts of this talk, because at least 2 times I was talking in Warsaw on various occasions. So yeah, if at some point it gets boring, you can also tell me and I will speed up or tell something else, because I mean, it is actually a part of a bigger story. I just give you some keywords here. It is not really a plan, it's kind of a cloud of topics that I have been doing since maybe last 10 years. We are trying, so me and some people, so the names are on the bottom of the page, we are trying to figure out what is the correct geometry in different mechanical physical systems. And somehow the word Dirac pops up pretty often. And yeah, but to all this, there was also some kind of prequel. You might have heard something about symplectic integrators, and you have for sure heard about symplectic and Hamiltonian systems. At least in this room, I don't have to elaborate a lot on that. So what I'm going to do today, I will start very, very slowly to tell you what I mean by geometric mechanics and why geometry is useful in mechanics on some examples that you know, that you learned in high school. And then I will go to Dirac and constraints, and this is the things that are marked in green. So I will at some point go to the algebroids and their cohomology that we defined as a tool to understand what is meaningful dynamics on Dirac structures. And all that we did because we had some numerical experiments that, okay, being honest, that didn't work as we expected. So actually, what is probably important in this talk, and there, do ask questions if you don't follow, I will tell you something about things that did not work, about things that we tried and had cumbersome results. This typically you do not publish. So if you read the papers that I cite, they will be a straight, smooth story. But to arrive to this straight, smooth story, we had to try things. So, okay, as a disclaimer, I would say this. Once again, if I'm going too fast or too slow, you can moderate it. If I tell half of the story, it's totally okay. I want to convey some messages. There are a lot. If it's only a part of it, I'm happy still. Okay? Those who have heard my talks, they have for sure seen this table, which is kind of philosophy or religion of what I'm doing in this community, with kind of 2 mottos. The first one is that geometry is useful to encode some physical properties, and this is what you see on the table. So the middle column is some mechanical or physical property of the system you want to study, conservation of energy, or what you mentioned right before the talk started, some dissipation or coupling. You may want to keep track of symmetries. You may want to keep track of conservation laws. And all of them, and this is pretty well established, or at least starts being pretty well established, they have some geometric interpretations. For example, you all know that conservative finite dimensional mechanics is somehow related to symplectic or Poisson geometry. Now, on the right of this table, in the right column, there is some color code. So some words are marked in green, I mean, I used to have more detailed color code, but that means that there is a numerical method behind it. So what do I want to say by that is that, yeah, sure, you have your continuous conservation laws. They're somehow encoded in geometry, and this is something that you learn in textbooks. Now you want to simulate your system. You want to solve the equations numerically. You will produce some discretizations. And once again, philosophy there is that when you produce a discretization that preserves the geometry of the system, you somehow automatically, let me be gentle there, do something nice to the physics of the system. The usual story people tell is you preserve, but there are subtleties, and I will stress the subtleties right away. Anyway, long story short, there is a second motto, is that when you are able to preserve this geometry, it is good for computations. Okay? So today, I mean, obviously, I'm not going through the whole table. I will only speak about the conservative systems, and I will speak about constraints. So we are in Poisson symplectic or Dirac geometry, maybe in the variant if time permits. I will mention something more, but let's cross the bridge when we come to it.
Sorry, Vladimir, one question. Have you done anything really about almost Dirac? Because I was interested, well, I'm interested, and some of the people here are working on modification of Dirac structures. Do you have anything about that?
Yes, I
Could
have
you comment
some.
briefly?
Yes, I think I have something. Maybe let's come back to this question in 35 minutes.
Hey,
When I
okay,
give you
great.
when I give you Dirac,
Yes.
which you probably know, I will tell you what works in Dirac, what does not, and then I will tell you what happens to the
Okay,
almost
great.
Dirac. Okay?
Because it will be interesting. Thank you.
Okay. So the first thing, and yeah, this is how I would present it to engineers, because I teach some course to PhD students in my university, which is about multi-scale modeling, and people who come, they are really doing applied stuff. So at some point you want to explain them, some people with no geometric knowledge or very, very little geometric knowledge, what is our science good for? Well, usually I start with some finite dimensional but big model, and what you see on the slide is just molecular dynamics with a lot of potentials. You would tell a story about it, and then I would ask a question. So these are the equations of motion. What can you say about the total energy of the system? Usually, if they have never seen any Hamiltonian or Lagrangian business, they will say, okay, let's try to compute. Then I say, great, I have a coffee, you compute. I come back in half an hour. But obviously, I would torture them for half an hour. I will say, these equations have some structure. And this structure you all know, right? Either you can rewrite them in the Lagrangian form or in the Hamiltonian form, and then either you plug your Lagrangian into the variational principle, you get equations of motions, they satisfy some nice properties, or you have a Hamiltonian, you plug it into a symplectic form, you recover some equations, they have some nice properties, and in particular, the energy is obviously conserved. This is really a high school example of geometrization of mechanics, right? I think you have all started your talks about geometry and mechanics like that. This is already useful, right? I give you two high school examples, a harmonic oscillator on your left, a simple pendulum on your right, a physical pendulum, and there very easily you say, okay, this is the energy, it is supposed to be conserved, and what? Then back to my engineers, I say, could you draw a solution? Right, and obviously you can draw a solution. So for the first one, you get the usual phase portrait, right? And all the trajectories are the same. For the second one, we will recycle it in what follows. You see there are like three types of trajectory. These circular ones that is actually the same, right? There is the green and the red one that corresponds to rotation of your physical pendulum, and there are this separatrix type, right? This which corresponds to a full turn that happens in infinite time. Why am I telling you this? Because this is something that you can really touch by hand. So I will forget that I can actually solve and draw it, and I will try to do numerics about it. So how do you do numerics? If you have never done it, you take the most naive thing you can imagine. You replace your right-hand sides by some finite differences. Am I going too fast about these words, or they are understandable?
It's okay. This is stuff, useful stuff. So it's
Yeah, this is the usual stuff. So you have Hamiltonian equations, and then you say, I cook up a discretization, which is called explicit Euler, where I just iteratively will compute the points on my phase portrait. And you have most probably seen this animation at some point in your life. So what is going to happen? What do you want to see? You want to see the ellipse that we have drawn, but you are going to see... No, you are not going to see. Let me try again. That always does this. Okay. You are going to see this, right? And if you see this, you will tell me, but sure, Vladimir, that was obvious from the very beginning, because what I am actually doing is I'm on this curve, and I take the tangent vector, which is given by these right-hand sides. I multiply it by some finite interval of time. So obviously I go from the curve. Then people started thinking, and I spare you the details, but actually there were some very random discoveries in the world of numerics some 30, 40 years ago. They started just modifying this discretization by hand. So you see the difference between the three that are on the slide. Sometimes you try to use things that you do not know to compute them, right? And sometimes you mix them. So that first one is called implicit Euler, and the last one is called symplectic Euler, and you obviously have guessed the reason. So the implicit Euler will do what? People who did not know, what would you expect?
the symplectic method that it preserves the energy, so it will be okay now to go. Yeah.
Yeah, we will come to it. Now I'm in implicit Euler. So you see, I replaced this. Yeah, what will
okay.
it do? Well, I mean,
I already have read of this stuff, so I'm not.
Okay, so you saw it, but those who didn't see will see now, and they will say again, but it was obvious. Okay, if they see, I don't know why it always stops. Okay, now I'm really not happy. Okay. Okay, that was the implicit Euler. So you see it spirals in instead of spiraling out. And now you meditate on it for 10 seconds, you say, but it was obvious, right? Because this is just the same method, but time reversed. And symplectic, well, this is where the religion is a little bit wrong. So naked eye, you would say it preserves energy. Now let us understand why it does not. And you're supposed to be surprised now a little bit, right? So if you do these applications, yes, this is the usual mantra. You say, I'm symplectic, I preserve energy. At this level, I preserve the area of my phase space. Hence, I preserve the level surface. And this is actually something that people in the engineering sciences are used to see if they do some fancy numerics. So they say, okay, these equations, they have some structure. There is some antisymmetric matrix in the game. I'm just rewriting the canonical Darboux coordinates in one chart. Then there is a skew-symmetric non-degenerate form associated to it, which is, in this example, just the oriented area or sum of oriented areas. Then the flow of my system preserves it. And this purple thing, so this is actually how they tend to define a symplectic flow. Have you seen this?
Yeah, sure.
Sure, okay. But you see, this is not something that you are used to do in differential geometry. This is very, very explicit. You have some metrics and you have gradients on the left or the right. Keep this formula in mind. It comes handy at some point. So now what we are used to see as geometers is symplectic mechanics in this context, where you say the preservation of the symplectic form is just this, right? The Lie derivative of the Hamiltonian flow of the symplectic form is 0. Then let me ask you two questions to which you obviously know the answer, but probably didn't really put it into the context of what I'm doing in numerics. So the first one is, if you have some vector field that preserves a symplectic form, can you say it is Hamiltonian? And if you can say that it is Hamiltonian, can you say that it is canonical in the sense of Darboux coordinates?
Well, you know, this maybe everyone knows. It's locally Hamiltonian is the derivative. If the first cohomology is 0, then it will be Hamiltonian. And the form of the canonical, it depends, because it has a 0, something like that, you will have no canonical form. If otherwise, you can put it in a rectified form, and you can always put the symplectic form or related to
Right, right. But now imagine you are a computer guy, right? So all these steps now need to be constructive. So
you will have a problem.
You will have a lot of problems. So first of all, the second question, you say there are Darboux coordinates, so as soon as you are symplectic, non-degenerate, etc., you can massage it to good coordinates, provided you are able to integrate the flow. So it somehow bites itself by its tail, but actually a bunch of flows. Then you would ask yourself, do you really need it? And we will see it. And for the first one, the answer is obviously correct. And if I come back to this slide, I'm on a space, so everything is contractible. Locally or globally, I am Hamiltonian. But eventually, with respect to a different Hamiltonian function. And this is a very important subtlety, so just digest it. You say, I discretized my flow in such a way that it preserves the symplectic form. So it is Hamiltonian, but probably with respect to some other Hamiltonian function. So you preserve an energy, but not the energy you started with. So when I said naked eye here, it still works. It still works because there is a bunch of results of how these two Hamiltonians are related to each other. And the phenomena, which you can prove, and you can prove that it is very persistent, is that your discrete Hamiltonian will oscillate around the level of your continuous Hamiltonian, and oscillate in a very thin band, which is controlled by the time step of your numerical method, by the order of your numerical method. Okay? So the upshot from all these things that you used to have as a baby example is that, yes, you do preserve the geometry exactly, then you are able to say something nice about your physics, but not necessarily the exact conservation of what you want to conserve. Okay? And this is a very classical story for instance, symplectic integrators. They are probably older than every person in the room. But if you do this for Poisson geometry, then you can get into trouble. And my PhD student solved some issues in like a couple of years ago in that context. So what is the trouble? If you are on a Poisson manifold, you are willing to say the same thing. You say, I want to preserve the Poisson bracket in some sense, and then I want to guarantee the energy conservation. The problem is that now your Poisson manifold has some extra structure. So what I'm trying to represent here is the Weinstein splitting theorem. So every Poisson manifold is foliated by symplectic leaves. So being in Italy, I'm doing some crime here. I am saying that I have a lasagna which is potentially singular. So that chef dropped a grain of rice into it. And this is causing trouble. So why is it so? Because if you just want to follow the symplectic leaf and you make a small mistake, small error, and you run into the singularity, then your dynamics is completely screwed. You might have seen some papers, and they pop up every once in a while, where people say, oh, we invented the Poisson integrator, which basically amounts to that. You restrict the Casimirs, you restrict your dynamic to a symplectic leaf, and on that symplectic leaf, you do symplectic integrator. Well, it's not that simple for several reasons. First, once again, it is almost never explicit, the splitting. And second, it does not survive the small perturbations. So what Oscar did is some kind of desingularization of this picture using groupoids. I don't know. I don't have time to give details, but it kind of deserves maybe a separate talk if you have never seen it. Okay, so kind of advertisement. And this is recent. Yeah, this is surprisingly recent.
Vladimir, there's one comment because you are talking here about the symplectic, for instance, Poisson structure. But you know, the problem is that, for example, at the beginning, when you start with the Hamiltonian, you want to make an approximation. The example you did works pretty much well because the levels of the Hamiltonian functions, they are well defined, they are compact and things like that. But if you had some Hamiltonian, it would be, for example, an hyperbolic function depending on the coordinate the momenta, then a small change in the Hamiltonian can make the evolution description.
That's exactly why I'm showing you this, right?
Yeah.
This is really a baby example where things could get wrong.
Yeah,
and I will recycle it for Dirac too, because this is where things do get wrong, despite the fact that you behave nicely in geometry. So yeah, really, I'm now going into that kind of subtleties where you say, yeah, the general approach, the general philosophy should kind of work, but in real life, you need to still be careful. This is exactly the things that...
example.
And you see, it is small. You know the solution, but... Yeah, so, okay. Once again, this is kind of folkloric. That was the starting point of the discussion.
Yes, sorry, just to make sure, do I understand correctly that your PhD student introduced some kind of desingularization procedure for Poisson manifolds?
The keyword is symplectic groupoid or birealizations. And this is exactly the way to puff up the space to reduce the singularity, to remove the singularities in some sense. And then there is a procedure of effectively computing this. So basically you enlarge it, you make a step and you project it back. And for a huge class, it is computable. Well, there are details. There are some case-by-case stories, but this is kind of a new point in the history of Poisson integrators.
Okay, very interesting. Thank you.
Welcome. Yeah, and then another piece of folkloric knowledge, I think this room I really do not have to comment on it, is about Tulchev triples. Right? If I need to comment on, just protest now, otherwise I flash it. So the idea is that you have a geometric interpretation of this dictionary between Hamiltonian and Lagrangian mechanics, and you can also say where the Lagrangian and the Hamiltonian and the differentials live. These are these double bundles, this T star, and T star, T star, T. And what Tulchiyev did, which is probably written nowhere, but is part of the folklore in the community, he said that all these three guys are symplectic and there are natural symplectomorphisms between them that I will use in the Dirac construction. If you need details, protest now, or I just turn the page.
Let young people talk, because for people having several years in Warsaw, it's impossible not to know. But for students, I don't know. So if any one of you don't know and wants any detail, please go ahead. Could be a good moment.
Yeah, so can you tell me? Did I lose the sound?
Okay, maybe you can continue.
Okay, I'm continuing. There is no protest. Okay. Yeah, so what we want to do is do this for a larger class of system. And the first and probably the main example would be systems with constraints, where I will tell you how Dirac structures come and why they're useful. So what is a Dirac structure? I just parachute it on you because I will have no time to do the motivation. So I take the direct sum of Tm and T star m. The history behind is that people wanted to study Lagrangian and Hamiltonian mechanics or study the velocities and the momenta. They are somehow related, and it turned out that just doing this is not really enough. However, the structure appeared. And so on this direct sum of bundles, you have two natural operations. The first one is the symmetric pairing. This guy that takes you two sections of it and gives you at each point a number. And another thing is this Dorfman bracket, or sometimes Courant bracket, which takes a couple and gives you a couple. So on the level of vector fields, it's just a Lie bracket, and on the level of differential forms, there is some operations. So operation that, if you know, is related to graded symplectic manifolds. If you don't know, just take a formula. This thing generalizes symplectic and Poisson structures in a kind of unusual way. So if I take Tm and T star m and look at the graph of a Poisson bivector, then what will happen is this symmetric pairing will vanish because of the antisymmetry of the bivector, and it will be respected by this Dorfman bracket because of the Jacobi identity for the Poisson bivector. And this is exactly the definition of a Dirac structure. So some sub-bundle of this big bundle, which is maximally isotropic, so the thing vanishes, Lagrangian, and it is closed with respect to this bracket. For the symplectical or presymplectic example, you will take the graph of a two form, and once again, because of the antisymmetry, it will annihilate the symmetric pairing, and because of the closedness of the form, it will respect the set. So it generalizes symplectic and Poisson geometry, but not in the sense that every symplectic is Poisson, but in the sense that they are acting in two different directions. Okay? And there are other examples. I usually like to show this picture when I talk about it. First of all, to brag that I know all of them except the guy who actually introduced the Dirac structure. And second of all, to say that there is a huge confusion in the term Dirac, right? So they actually used this name to make some kind of fashion, but it is not necessarily related to other Dirac constructions that appear in literature, like and this is especially confusing when I'm talking about constraints, because there are Dirac constraints, but this is not what I'm going to say. And the word was invented for commercial reasons to make the science fashionable. But okay, going to science, actually, the first example is you look at systems with mechanical holonomic constraints, and then you recover Dirac structures. How do you do this? So what is a system with constraint? It means that at each point of your configuration space, not all the velocities are permitted. And you can also say that maybe not all the points of your configuration space are permitted. Geometrically, it means that you have a distribution in TQ, so this guy. Now, for the distribution in TQ, you have some natural operations. First, you can pull it back to T star Q. You see the diagram on the left. And you can look at the annihilator of what you have just pulled back. So these are two important ingredients. And also remember that in this T star business, there is a canonical symplectic form on T star Q. So what we are going to use now, the Dirac structure in the game is written below. So you take couples of vector fields and one forms. These vector fields, they are allowed to live in the pullback of the distribution that defines your constraints. And the one forms, they are reduced in two ways. Either they are in the image of that symplectic form, or they are hooked up in such a way that the whole thing is in the annihilator that we have just discussed. And I am saying that this is an almost Dirac structure for a reason. So in this definition before, if I drop this condition, this closedness with respect to bracket, the thing is called almost Dirac structure. And probably, Javi, this is your question, right? You want this somehow at some point.
Yeah, because there are several cases where this is not necessary, but you can still do this stuff. I mean, you have twisted Dirac, you have quasi Dirac, you have almost Dirac.
Yes. So in this concrete case, you are Dirac if your constraints are holonomic, and this is just a theorem. So this almost Dirac structure is Dirac when your initial distribution was integrable. Some things of what I'm going to tell now still work when you don't ask for this condition, and some fail miserably, and this is what I'm going to tell you about. So, okay. Also, I don't know if younger people have never seen this definition. The first time you see it, you don't understand what's going on. Let me draw a picture. The picture is usually more understandable. So you are at the point on your phase manifold, for example, and in this pullback business, you authorized only some directions. So this green curve or green line, so green line in the tangent space or green curve on the manifold, is the dynamics that you authorize on the phase space. Now you have this symplectic form that maps it to T star. So this green line here, and they are underlined right here and there. But as mentioned, it should be maximally isotropic. So the dimension somehow doesn't fit. You need to complete it, and you complete it precisely by the thing which is missing. So this red thing lives in the annihilator, and you just put it here. Okay? This is the geometry you would like to have in mind. Yeah, and then when you can integrate it to a submanifold of M, then things survive the bracket. Okay, now this is, so to say, kinematics of your system. If you want dynamics, you need to do something about the energy. So you use the Lagrangian, and as we saw in this Tulchiev picture, you naturally recover some things that would live in T star of these guys. And using these Tulchiev isomorphisms, you would recover what people in the literature call Dirac differential, and I strongly insist of not calling it Dirac. There is apparently a geopolitical quarrel around it, so I suggest to call it Tulchiev differential. So what is this guy? You take dl, and you apply a combination of Tulchief isomorphisms to end up in T star of your phase space, so your phase manifold. And then the dynamics is something that lives in the T of your phase manifold, so a vector field on it. And these two guys should talk to each other, so they go to this Dirac structure that we just defined. Okay? And people call this an implicit Lagrangian system, so this data of a distribution of a Lagrangian and this partial vector field that defines the dynamics. Now, you do things in coordinates. If you have never seen this and never done it, it's a nice exercise. You do it in coordinates, and you recover 4 conditions of these two guys living in the Dirac structure. So the first one is this. This is just meaning that a momenta is given by a Legendre transform. This one says that the velocity is the derivative of your coordinate. Well, the velocity is the velocity. Good. This one says that your velocity belongs to the distribution, so it is authorized by your kinematics. And this interesting one of someone belonging to annihilator, right? This guy tells you that your left-hand side, which looks like this, is proportional to some one forms. And you look at this carefully, you recognize Lagrange multipliers. Okay? What is the output? We got some geometric picture, we constructed a Dirac structure, and for free, without doing any variational calculus, any constraints, any imposing constraints, we recovered the usual equations that we would treat in the Lagrange multiplier business. You could say all this for that. Well, no, because then there is the second step when you discretize them. And you discretize them in some kind of way. So on the top of the slide, you have what I have just said in the continuous world. Then you introduce a discrete Lagrangian. So this guy is something that looks like the continuous Lagrangian, but now is evaluated on the approximations of your dynamical variables. And for the approximations, you use this discrete equation. So there is some kind of iterative process that now connects coordinates, velocities, and momentum. We pay the price, right? We are treating more variables than we had initially, like 1.5 more. Let's see what we gained. Let's go to this simple example. I'm just doing what I have said for a simple system with one constraint. So I'm taking this physical pendulum, but I forget that I know the trajectory, and I forget that I can parameterize it by this angle. So this I do not know. I just say I am in R2, and I have this constraint that the distance to the center is fixed. The distribution is obviously integrable. It is generated by one vector field, disk psi. It is in the kernel of my d phi, which, once again, if you have done this Lagrange multipliers, at some point you have obviously seen. And then you do this business. So the Tulchief differential, you write everything in coordinates, and you get this kind of usual equations of motions with constraints. You discretize them, and this is what you get. So what would you learn from these pictures? If you take the method that preserves the Dirac structure up to order 1, and you compare it with Euler with the same initial conditions and the same time step, you get 2 different pictures. You see, this is a pendulum oscillating. This is a pendulum rotating. And then you think about the energy level and you realize that this one is the correct one. So you see, doing these operations, what I gain is at least the qualitative behavior. But you kind of see that the constraints is still not completely preserved. So it sweeps some band, some finite band, which is it is not really supposed to do. Then you try to improve it, like the order of the numerical method. You compare this Dirac first order with Dirac second order, and you see that then the Dirac second order recovers what you expect to see from the dynamics. Again, I will have to say naked eye at some point, but at least this is what you do at least to motivate why this is going on. Now, what we did, we compared it with other fancier numerical methods, because obviously nobody uses Euler in real computations, and it turns out that Dirac-based method, being pretty cheap, are behaving very well, especially knowing that they do not imply any resolution of algebraic equations. So the cheating word in the bracket means that actually we got rid of the Lagrange multiplier by substituting the explicit formulas into the equations, which is, you need to be lucky if you can do it by hand. And another example is probably a more serious mechanical system. So you take a beam and you fix it in some supporting mechanism, and you start pressing on it. So the mechanical phenomena that you want to capture is called buckling. So at some point, it will stop resisting the pressure and it will kind of bend on one side. And this is a very nonlinear effect. So it happens, it's kind of a catastrophe. I'm showing the picture for a very simple model where I just attach two pieces of it, so a very simple discrete model, but it can be done for more reasonable discretizations. So then you see these ugly pictures. What do I mean there is that the picture on the left, it is still buckling but oscillating. The picture on the right, it completely broke and started rotating, which is like totally non-physical. And in contrast to the one before, you have no a priori knowledge about the actual behavior of the system. So both are satisfying some energetic properties, so you cannot tell the difference. And even worse, if you do reasonable numerical methods, then you have still to choose the correct one. So you see, this is the comparison between Dirac second order and Dirac first order. Well, there you could say, sure, second order should be better, and it is better. So you see, you get some borderline oscillations that are not going into rotations on the left. There are even funnier subtleties, like it has two equilibrium points. One is vertical and one is somehow banded. And there, once again, you have no a priori way to distinguish. So there is no a priori law that tells you that one is better than the other. And this is where I would say, okay, the better Dirac is preserved, the better is your physical simulations.
Sorry, may I have a question?
Yes, sure.
So there is no way to simulate it using Runge-Kutta method?
Okay, first of all, Runge-Kutta, you still need to incorporate the constraints somehow, right? So you end up with an algebra differential equation, right? You need to impose it. If by chance you can resolve it, so you can exclude some variables to put the whole dynamics only into differential equations. Yes, then you can do. And this is the comparison before. But in general, no, you need to do something about algebra. Okay. But it is a tricky question, because also Dirac will not do miracles when there are no miracles. What I'm saying is that even where you can do it by hand, where you can resolve it and do Runge-Kutta, Dirac is very competitive. I mean, in principle, should have this talk happened like 5 years ago, I would just say, okay, Dirac is doing great. But then we tried to improve it and to actually understand why these discretizations are as they are. What I totally hid under the carpet, and you didn't ask because you had no reason to ask, some reason, trust me, I don't know why. So I had made some choices here, right, in the discretization. Like before in the symplectic business, there are sometimes things that depend on the variables which we know. Sometimes they depend on the variables that we want to compute. There is some choice for the discretization of velocity, which I, again, totally parachuted on you. You might have asked why. And in the momenta story, for example, I could have said, okay, I know that when I am Dirac without constraints, I want to recover symplectic. That fixes the upper part of the transparency, but that says nothing about the lower part. And the lower part was, again, in fact, causing the trouble, which we understood by trial and error. So another PhD student of me was doing the following. She took a method from literature that was called Dirac preserving and started doing the usual things that you would exploit to increase the order of the method. Basically, you you cut the time interval in two, and you iterate the process in such a way that both flows preserves your structure. And in the symplectic business, it helps you to actually build a higher order method. And it turned out in the simulations that it didn't work for Dirac. And it didn't work for a reason that it was actually not geometric. So it was not preserving the Dirac structure exactly. And back in the days, we didn't really know how to do it. So it turned out that we didn't know how to preserve it exactly. And at least we wanted to be operational, so we introduced some keyword, which is pseudo-geometric integrator. And there, you will have to specify the orders. So you remember, in the symplectic business, I told you I preserve the form exactly. Then I guarantee the energy preservation up to some error. And the order of this error depends on the choice of the discretization. Now, I am spoiling the geometry, but in the controllable way. So I say I preserve a Dirac structure by hand up to some order, and there is a constructive procedure behind it. I mean, it's basically juggling with polynomials and computing coefficients, which is totally formalizable, and kind of even computer algebra can help. But then you say, at the next time step, I want to preserve this geometry again at this order. Then you can guarantee that you preserve your physical property, and in this case, constraints, up to some order, but potentially some other order. And it turned out to be a correct word to use. So we realized that the methods that we saw in the literature, which is from Martin School, were not doing what we wanted them to do because they were, in our language, pseudo-geometric of order 1, 2. So first order conservation of the Dirac structure implying second order conservation of the constraint. What we made as an improvement were, well, better, but not dramatically better. So they still were not geometric in the classical setting. But okay, at least the positive remark is that we were finally able to control it. Again, for commercial reasons, I could have told you, well, great, we are done, but this is not in the philosophy of the table. We still do want to preserve this geometry exactly. Okay, maybe this is the place where I can make this remark, Javi. This would work for almost Dirac.
Oh,
kind
great.
of out of the box. So what she was actually doing, my student, she was also doing this for non-holonomic constraints. They taking more or less by hand constructed discretizations and applying this to Chaplygin sleigh or to some rolling ball.
Vladimir,
yes, was given better results.
Yeah, yes, a general comment out of getting out of topic, but for every differential equation, the methods, available methods to make discretizations, well, there are lots of, and everyone is looking for the different things. Yeah, I mean about certain conservative integrability condition. As you do about geometric structures, about I mean the decisions to obtain to choose a discretization, there are lots of. So it's each one has its own advantages. And this is just a general stuff, yeah, because they are always saying why the discretization on another one, and it's a big stuff. It's a big problem there.
Yeah, exactly. No. That I agree, and that I think is part of general knowledge now, so that there is no point of arguing about it. Okay, I feel that I start running out of time, and I still didn't go to the fancy stuff, which I want you to, well, I want to walk you through that results. So basically, what we wanted to say, how do we do this in a proper, honest geometric way, and the way out would be to do variational integrations on Dirac structures. But for this, and this is the main result of the paper I cited in the abstract, you need some variational formulations of dynamics on the Dirac structures. I don't know if you noticed it or not. If I don't stress it, there is a conceptual difference between symplectic or Poisson Hamiltonian mechanics and this Dirac structure-based story. So when I was presenting this simple examples of Hamiltonian systems, and I was saying that there is symplectic discretization, there was always a fixed symplectic form, so some property of the space. And then you were putting inside the dynamics of the physical property of the system. You were kind of putting the system into the space that had some geometry. Now, in the constraints business, for example, you were reading off the geometry of the space for each system. So it was potentially different every time. And that conceptually I didn't like. So I dragged into this story for more people, and I started asking questions like, okay, I give you a Dirac structure. What is the piece of data I need to give you in addition to define dynamics on it? And when I say dynamics, define some variational principle that will reduce to the equations of motion that are physically relevant. And the answer is in this paper. I will just in the infinite speed walk you through it. And for this, you need some pieces of mathematical data. So I told you that these Dirac structures are subbundles of Tm and T star m. There is a general picture how to describe any Dirac structure there. It is about some involutions when you identify Tm with T star m using a metric. And then there are eigenspaces in this flip involution of this in this identification. And it turns out it's pretty easy to see that then an almost Dirac structure is a graph of an orthogonal operator acting from Tm to Tm. So that picture that I was drawing is just a little bit tilted. And there is, again, a map that goes from one to another. And if you want to be an integrable Dirac structure, so not almost but honest, then you have to impose some nonlinear Jacobi type integrability condition. And maybe an important remark here is that you can introduce a Lie algebraic structure associated to this Dirac structure, and it is done explicitly in coordinates using this orthogonal operator. So this is one piece of data. Then the data about Lie algebraics is that that I really want to skip. So I kind of assume you know something about Lie algebraics in this room, or protest.
You can.
I can. So you know Lie algebraics. Then I just give you one fun fact: is that when you have a Lie algebroid, you can look at the image of the anchor map, and this always induces a singular foliation on the base. And when you restrict your Lie algebroid structure to the leaves of these foliations, you also get Lie algebroids. Then we defined an object which is called the horizontal cohomology of Lie algebroids. So you look at the image of this anchor map, and you look at vector fields. Oh, okay, yeah, let's say vector fields. Elements that are in the kernel of this anchor map, and then look at the differential forms that are annihilated by those vector fields. Or if you do it in the neighborhood, you also look at the differentials of these vector fields that are annihilated by this differentials of these forms that are annihilated by these vector fields. So these guys are called horizontal forms for the algebroids. And then the cohomology is what you think it is. So there is a natural differential on the Lie algebroid that again restricts to every point where you need it to restrict. And you look at the kernel of it, model of the image of it. So this is what we called a horizontal cohomology. Now, why I'm telling you this? Because when you look at horizontal forms on these leaves of these foliations, you can glue them back. So basically, there is a dictionary. There is a way to say, I have a form on a Lie algebroid, or I have a bunch of forms on the base. And if they are horizontal, then I can go up or down. And I can make computations either in the Lie algebroid setting with the appropriate differential, or I can make computation downstairs using just Dirac operators. And all this applies to the Dirac structure. So you remember there was this symmetric pairing. There was some kind of coupling between vector fields and norm forms that was used in the crossway with a plus sign. Now you do the same thing with a minus sign. You get an operation that eats up two vector fields and which is antisymmetric. So it behaves like a two form. And you remember to any Dirac structure, you can associate a Lie algebroid structure. So this guy, it is easy to check, is the horizontal form on Dirac structure, so on a Lie algebroid that is constructed. And then you can repeat what I have just said. So you can foliate the base, you can glue it together. Basically, what you are doing, you are gluing presymplectic manifolds into a Dirac structure. Yeah, and then this two form is actually the abstraction class to the existence of variational formulation. So if this thing, if the class of this form vanishes, then you can integrate it, you get a one form on a Dirac structure, and the answer is that your curve on a Dirac structure is, well, for example, in one setting is Hamiltonian, meaning that this kind of thing is satisfied. If and only if it is an extremal curve of this functional. So in this functional, you have two parts. One is given by the geometry of the space, so this primitive of this two form, and one is given by the physics of your system, the Hamiltonian that you give yourself. So this is kind of one answer to my question. Now, the second answer, if you want the Lagrangian description, there I just flash it for 1 second. You do the usual to achieve business about Lie random transform, etc., etc. You do some usual constructions about Dirac structures, like how you pull them back and twist a little bit by symplectic form. And then a very similar result. So if this two form, its class vanishes, then you integrate it, and you get, again, a very similar expression of some geometry of the space, and a familiar expression if you have done it for just usual Lagrangian systems of the dynamics of the space. So this is the data of the physics of your system. And then it is the same as saying that some curve belongs to the appropriately chosen Dirac structure. Okay? We discussed with the Grabowski, who introduced similar but not coinciding objects on Dirac algebroids and on general algebroids. And well, it turns out that at least for the constraint systems, they reproduce each other, but they kind of go in two other directions. There is a recent example where, once again, I'm just showing it, which is due to Valery Kozlov, like this year, more or less last year, where he seems to reproduce in this context, but not realize in this context, the Poisson dynamics, so variational formulation of some Poisson Hamiltonian dynamics, which is, again, a long-standing question. It is a particular case, so it doesn't answer all of them. Yeah. And well, then in principle, I'm supposed to tell you what follows, and what follows is still in progress. So let me go here. Since I mentioned this Poisson example, you might want to use the Dirac structure associated to your favorite Poisson example and check what happens in this Lie algebroid cohomology business. And it turns out that some of them work out of the box, but some of them, and those are physically motivated, are just not satisfying this condition of the class vanishing, which, well, is unfortunate, but maybe not dramatic. We want to have some more details in this specification to the Poisson result. But then related to your question again, Javi, if I want to do the same for almost Dirac structure, I run in a bit of trouble because my class is not defined. So my cohomology is not defined. This closing of the bracket was exactly equivalent to the differential square into zero. So now I don't have it. I cannot define properly the cohomology. We need some twist of it for a very simple reason. Actually, when I say abstraction, is some kind of language abuse. It means a condition. It is sufficient, but not necessarily necessary. I managed.
But Vladimir, as you said, because I think they're good, that you need a twist of it somehow, yeah? So do you have an idea how to deal with it?
We have some examples. One keyword is maybe economic constraints, which is instructive, but which is... so it's kind of, by definition, something that admits a variational description.
I know because I worked in economic mechanics a long time ago.
I know.
This is the thing that's about doing many topics. Okay.
Yeah. So at least this is the first one on the list, and maybe some inspiration for it could be good. And once again, those things like case by case examples, sometimes you just recover this variational formulation, but you don't really understand why. So what exactly failed in this process? And then one huge parenthesis in this story is still this discretization, which is open, but which is very close to being closed. So what we are doing, and that's kind of a machinery. So you just take the most general variational principle, not in the sense of mechanics where you say your Lagrangian depends on Q and Q dot, but in the sense of Pontryagin maximum principle. So where you authorize everything with algebraic conditions, with any mixed conditions, and you discretize that. Surprisingly, people haven't done it. And this seems to apply out of the box to this variational formulation now. So as soon as this is done, that would produce an honest variational integrator, so honest geometric integrator for the Dirac structure, at least for the integrable Dirac structure. And then, the next natural step is what happens in this almost geometry. So what you can relax to still obtain the variational formulation. And I think I'm over time already. I'll just flash one more slide saying that there is another huge parenthesis about this being infinite dimensional, because we were talking about ODEs, but when you talk to real mechanics people, they want PDEs, they want continuous media. And there it's even worse because some words are not defined. But surprisingly, some case-by-case things work. So to be continued, and I hope that at some point I will tell you more on this page. And yeah, I'm usually thanking the audience in the local language, but the seminar, I don't know where we are. So I decided to take the languages of the organizers, of the affiliations of organizers. Thank you for your patience, and sorry for going over time.
Thank you, Vladimir. Thank you. So, is there any comment, question, remark for Vladimir? Okay, I have one.
Go.
Listen, when you have the almost Dirac, is because the bracket does not close, but you can change the bracket as you said, and there are 30 classes of Dirac or related to Dirac structure, for example, almost Dirac and things like that. Many of them, they are related to the fact that the distribution, the projection of the subbundle in the generalized tangent bundle gives you a distribution that's integrable. I mean, it may happen that it's integrable, but it's not. Does it help to make all these cohomologies or whatever? Because sometimes when you do this stuff, for example, when the distribution is integrable, is locally regular, I think that it can be, for example, twisted. You can change the bracket, you can twist it to obtain an twisted Dirac, and many of the things work. Have you tried anything like that, or
yeah? Okay.
does it help, or?
When you say twisted Dirac, is twisted courant algebroid in the
Yeah.
I'm not sure that it helps immediately, but that's a nice idea. So let me say what I want to say. Actually, that took some time to meditate this idea. So when you are here defining the algebroids, I put it in brackets, but I didn't comment on it. So in principle, you don't have to be Tm plus T star M.
Yeah, as it happens when this, it's a more general stuff. You have a way to change to the tangent, cotangent,
Okay,
when it's a split, for example.
Yeah, okay, so yeah, and then there is the result that they can be under some conditions classified by this tree form, but this is provided that you are exact. So your projection to something is not degenerate. It seems that the examples that we have, for instance, in the Port-Hamiltonian systems, it seems that they are not in that setting. So maybe an idea is to look at this guy, but then the bracket is wrong.
Yeah.
So what I'm meditating now, and this is top secret, fortunately it goes on YouTube, right? I think that the correct thing is not to go to classification exactly immediately, but stay in this abstract E plus E star, hook up the bracket that is there, because you know the general definition. It is not this. It is a bunch of operations that satisfies 3-4 axioms.
Part of the talk can be that with a general bracket. The fact that it was the tangent cotangent, it helped with calculation and 30 parts. But I don't know how much, but to me it's more general. Yeah, but I don't know how far you can go.
Yeah. Let's be, my conjecture is that a proper choice of a bracket there could actually make it integrable, mimicking some other conservation law.
Yeah, this is in certain sense something that I try to tell. More or less. Say what is the essential thing that allows you to.
But I mean, my suggestion is not to go immediately to this Chevere class clue, but stay before that and see what happens there. Maybe there is some mechanics that gives you hints of what are the correct operations.
Yeah,
so
sure.
if you are curious about it, let's keep talking.
Yeah, sure. I would. First of all, please send me the other slides. It would be nice to have. And when you will have anything new, let me know if you have a paper or whatever, you have any
Yes.
good ideas.
Yes.
It would be nice to be in touch and to talk about it.
Yes.
Okay,
Great.
so
Thank
maybe
you.
we have to finish. It's any other question, remark, short for our speaker? No. So, Vladimir, thank you very much. It's been a very nice talk. I have had, and I think my colleagues too, a lot of fun. So take care. Thank you.
Thank you for inviting, and you too. Take care. Stay in touch.
Yeah, and I hope to see you in Warsaw soon.
Yep.